Hey everyone, and welcome to This Explainer. I am super thrilled you're tuning in, because today we're tackling one of the absolute most frustrating bottlenecks in modern software development. We're going to break down exactly how we can bridge that massive gap between highly creative, probabilistic AI models and the incredibly strict deterministic structural demands of software engineering. Seriously, if you have ever sat there watching a perfectly good data pipeline just crash and burn because the language model decided to output a polite little sentence right before your JSON object, well, this explainer is definitely for you.
Okay, let's dive into this. Here's our agenda for today. 1. The unstructured data problem. 2. Math of constrained decoding. 3. Pydantic, the schema blueprint. 4. Smart retries and feedback. And 5. Multi-provider abstraction with Instructor.
All right, kicking things off with Section 1, the unstructured data problem.
So here is the core issue we're dealing with. Probabilistic text generation is fundamentally terrible for deterministic databases. Notice the inherent tension here? It's like trying to fit a cloud into a rigid box. Language models naturally want to be creative, unpredictable, and yeah, they are incredibly prone to hallucinating new keys. But on the other side, our data architecture demands total deterministic schema compliance. We need strict schemas. We need hard data types. We need predictable pipelines that act like a solid brick wall to prevent silent data corruption. In the past, we all tried to fix this with crazy complex regular expressions, or, just begging the model in the system prompt to please, I'm begging you, just output JSON. But that approach, it's just fundamentally fragile.
The researchers over at did.do absolutely hit the nail on the head when they wrote this. Getting the right answer is only half the problem. Getting it in the right shape is the other half. This is an absolutely crucial concept to grasp. In a production environment, if you have a parser that works, say, 95% of the time, that's not just a minor annoyance. That is a critical vulnerability. That 5% failure rate, that means missing fields, type coercion crashes, and totally corrupted databases. So consistency isn't just some nice-to-have feature. It is a hard, non-negotiable requirement.
That brings us nicely to Section 2, Math of Constrained Decoding.
We're going to look under the hood at how native structured outputs solve this formatting headache right at the inference engine level. The real magic happens when we treat the solution as a mathematical absolute. So instead of just politely asking the model for JSON, the application hands over a formal JSON schema. The inference engine then takes that and compiles it into something called a context-free grammar, or CFG. Think of this CFG as a mathematical boundary. It's essentially a binary validation mask. During token generation, the engine computes this mask to filter the probability distribution. It literally forces the probability of generating an invalid token, like, say, an unclosed bracket or a random trailing comma, to mathematically 0. And it does this before the model even takes a sample.
And this brilliantly illustrates the difference that engine-level constraint makes. Just look at the comparison between the older JSON mode and the newer structured outputs in strict mode. With the standard JSON mode, you had a massively high validation overhead simply because the keys could hallucinate or fields could just vanish entirely. But with strict mode, the engine guarantees schema and key adherence natively right at generation time. Because it catches structural errors before a token is even sampled, your validation overhead drops like a rock.
Let's move on to Section 3, Pydantic, the schema blueprint.
So how do we actually define these schemas without losing our minds writing raw JSON? Well, that's where Pydantic comes in as our architectural blueprint sitting directly between your raw Python code and the API. But to use this strict mode, we gotta play by a very specific set of rules. As they say, you can't build a stable house if the bricks keep changing shape. To avoid having your API requests rejected right at compile time, your Pydantic schemas must adhere to these rigid constraints. First up, a mandatory required list. That means no true optional parameters. You have to define them as nullable instead. Next, explicit property bounds. Absolutely no unmapped keys allowed. Then we have complexity limits. You're capped at a maximum of 100 properties total, and you can't nest them more than 5 levels deep. And finally, the keys will generate in the exact preserved order you declare them in, which honestly gives you some awesome control over how the model kind of thinks step by step.
Now let's look at how local enforcement builds on this. Since the inference engine is handling those structural constraints during generation, it strictly rejects complex runtime rules. It is not going to let you use regex patterns or minimum value limits in the API schema. Because of that, you absolutely must establish local validation boundaries. The model takes care of the structural mold, ensuring fields exist and are the right data type. But your client-side Pydantic decorators like field validator and model validator, those are absolutely essential. That's where you enforce your actual domain logic locally, like making sure an end date actually comes after a start date.
All right, heading into Section 4, Smart Retries and Feedback.
Because what happens when that local validation fails? Consider this question for a second. What happens when the LLM output is structurally valid JSON but semantically wrong? A schema guarantees that a value is, say, an integer, but it absolutely does not guarantee that a total amount actually equals the sum of its line items. Structural validity does not equal factual accuracy.
When things go semantically wrong, developers usually just loop a blind retry. But doing that is just throwing money and time out the window. I absolutely love this quote from Reddit user Fantastic Sid about feeding the error back to the model. They noted that this targeted feedback matches the training trajectory perfectly. Quote, "Clanker messes up, human yells at Clanker, stupid robot gets it right second time around." It's hilarious, but it's true. The model needs to be told exactly why it failed so it can edit its work, rather than just rolling the dice again and hoping for the best.
So here's a highly actionable 4-step blueprint for a self-correcting retry pattern. Step 1, extract only the specific invalid span of data. Step 2, provide the specific local rule that was broken. For example, tell it, hey, this value must exist in our database. Step 3, drop the model's temperature to 0 for the retry. And step 4, rerun the request with constrained decoding still active so it doesn't accidentally invent a brand new structural error while trying to fix the semantic one. This targeted feedback loop will save you a ton on API costs and drastically improve your pipeline's reliability.
So the crucial point is really how you manage this feedback. Advanced error handling requires a few key things. First, mitigate cognitive anchoring. If you feed the entire broken JSON blob back to the model, it will often anchor on its own mistakes. It might fix the one field you yelled at it about, but keep all the other broken structures. So only echo the specific broken span. Also, handle truncation properly. If a response gets cut off because it hit the max tokens limit, it looks like a schema failure, but it isn't. Don't retry, extend your token budget. And finally, always observe your telemetry and check for safety refusals before you even try to parse the data.
Which brings us to our final stop, Section 5, Multi-Provider Abstraction with Instructor.
We've built this incredibly robust pipeline, right? But tying it strictly to just one provider's SDK is a massive operational risk. Enter the open-source library Instructor. It unifies diverse AI backends under a single, cohesive Pydantic workflow. Whether you're routing over to OpenAI or Anthropic using their native tools modes, or Google Gemini, or even a local open-source model via Llama using JSON schema, Instructor dynamically maps its extraction modes. The beauty of this is that you write your Pydantic extraction logic once, just one time, and you completely avoid that crippling vendor lock-in.
And of course, abstracting your providers means you absolutely need unified observability. Keeping visibility in production means ensuring your telemetry correctly instruments all these new structured endpoints. Standard OpenTelemetry GenAI tools now wrap the parse helpers to intercept these inputs. When they detect a Pydantic model class being passed through, they automatically record the output type as JSON. This exposes the structural metadata, the token usage, and your performance footprints right in your tracing dashboards. It is literally a lifesaver to get this level of visibility so easily out of the box.
Well, we've covered a lot of ground today, and I want to leave you with this final thought to chew on. As natural language increasingly becomes our primary querying tool, are your data pipelines truly ready to filter the poetry from the parameters? By combining constrained decoding, strict Pydantic schemas, and smart self-correcting feedback loops, you can absolutely ensure your architecture is resilient enough to handle whatever these models throw at it. Thank you so much for joining me on this explainer, and happy building.